I'd like everybody to take your seats now. You'll have about 7 or 8 minutes after class to look for your midterm. And then you'll have all the time in the world to look for your midterm in my office during my office hours. So please take your seats. You guys who haven't found them yet, please take your seats so we can start class. You bet. I know. That's what it is. You got linear search, and that's all, because they're not sorted. So can I have your attention? I just want to say a few words about the midterm. Everybody should see their score on eCommons. Match it and make sure there wasn't a clerical error or something like that. If you didn't get a chance to pick up your midterm, pick it up after class. Don't come up here while we're trying to lecture. And if you don't want to bother with any of that, you can just come to my office hours. They'll stay there the rest of the quarter. Even after the end of the quarter, they'll stay there if you don't mind waiting. If all you want to know is the score, it's on eCommons. Log on to eCommons. You should see midterm 1, and you should see the score recorded there. Now, I know the first impulse is, as soon as you look at your midterm, is to say, wait a minute, I got that right, or wait a minute, I don't understand why this lost so many points, or something like that. The time and place to talk about that is not right after you get the exam, or right before class or right after class. It is with the TAs. So the first step here is step 1. Read the solutions I posted and compare your solutions to my solutions. That'll help you understand why points were deducted. Then look at Piazza. They're going to post, or they already have posted, I'm not sure which, a breakdown of who graded which problem, which TA graded which problem, and what the rubric was in each case, or a rough outline of how that problem was graded. Go to the relevant TA and ask them your question. Why did this get loose points? Blah, 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 blah. If you're not happy with that answer, you can come to me during office hours and discuss the grading of your midterm. Okay? So that's the process for clarifying grading issues. That's the time and place. Let's see, I extended PA3 2 days. It's now due Saturday, 10 p.m. Is that going to be enough? Okay. So how about 2 more days? Okay. I don't see me going much further than that, if any. Okay, so that puts it at Monday, 10 p.m., which means you'll have all day Monday to get help. There are labs on Monday, aren't there? Let's see. We have 2 labs. We have 4 to 6 and 6 to 8, both at Crown. 4 different tutors are there for 4 hours straight after class on Monday. Okay, so that's a huge block of time. You can get all kinds of help from 4 different people. You can stay the whole 4 hours if you want to and get help from all 4 people. All right, so there are opportunities to get help if you need help. I strongly urge you not to go in there and say, hey, I haven't started it yet, can you help me? That's a bad place to be. All right, but it'll be due, so the door will close 10 a.m. Monday morning. All right, so let me note that fact. Remember, when I give a extension, hang on a second. When I give an extension, the 12-hour grace period goes with it. 2 more days. Okay. Any quick question I can answer about PA3? Go ahead. Yeah, Tuesday morning at 10 a.m. Right. The 12-hour grace period always travels with the extension. Go ahead. You can make as many helper functions as you want. I strongly recommend you write 2 helper functions. One to compute the dot product of 2 lists considered as sparse vectors, and one to compute the sum or difference of 2 lists considered, again, as sparse vectors. Does everybody understand how to do that and why you want these lists to be sorted in column order, right? They need to be arranged in column sorted order, increasing columns. So for instance, how do you do dot product? Why do you need dot product? Because row I, column j, you have to compute the dot product of those 2 vectors in order to get the ijth element in the product, right? That's the definition of matrix multiplication. Of course, columns are hard to get at, so you should first write transpose of the second factor in the product. So write transpose, so you take the ith row and the ith row of A and the jth row of B transpose, and you take their dot product. That's the ith row, jth column of the product matrix, which you're going to be building. All right? So you need something to compute this dot product. How do you compute the dot product? Well, the only time 2 numbers get multiplied is when their column numbers match, right? So you have to take 2 lists and simultaneously step through them using the cursor in each one. So go to the front of both of these lists, get the element at the front, and cast it as entry. Look at the column for each of those elements, and if they match, multiply the 2 numbers together and place that in an accumulating sum variable. You're inside a loop now. And then move next on both of them. If one of them is behind, you should march that one up until it either equals or surpasses the second one. So you should always be moving forward on the one that's behind. And by behind, I mean a lower column number. So lower column, move next. Keep moving next until that one gets ahead of the other one. And then move that one forward. And if at any point in this simultaneous marching through both lists, you get 2 column numbers that are the same, you multiply the values, put that in your accumulating sum, and then move next on both lists. Does everybody understand that? If you don't understand it, then you need to get some help, right? That's about the only sensible way to do this dot product. Go ahead. Yes? Was that a yes? Okay. That was a yes. All right. Okay, any other questions on PA3 that I can answer? The addition algorithm, by the way, adding 2 lists is a little bit harder because the output is another list, not a number, as it is in dot product. Now your question was, can I have as many helper functions as I want? What else do you want besides those 2? You're not paying attention. You who asked the last question.
No, that's all I wanted.
That's all you wanted, okay.
That's exactly what I wanted to hear.
Okay. Yes. Yes.
Thank you.
All right. Because sometimes people start building functions that make no sense, and I don't want that. Okay, where were we? We were talking about the recurrence relation handout, and we were about to start on the master theorem. By the way, I corrected a few things in this handout. You notice in this last step, this last example before the master theorem, I estimated downward. I got T of n was omega n squared, so T of n was theta n squared. And somebody pointed out to me, hey, Pat, you could short circuit that proof. So I went ahead and did that short circuit. So if you read the handout now, it's a little bit shorter. I just wanted to point that out. The master theorem. So the master theorem applies to recurrences of the form T of n is A T of n over B plus F of n. Now this is supposed to represent the runtime of an algorithm that takes a problem of size n, splits it into A subproblems, each of size 1/b, the original, f of n represents the cost of doing the dividing and the combining of the subproblem or subinstance solutions into a solution to the original problem of size n. A needs to be greater than or equal to 1. B needs to be strictly bigger than 1. Of course, it would have to be, right? Otherwise, your subproblems are not smaller. The whole idea in divide and conquer is to work on smaller instances of the same problem. So B needs to be bigger than 1. F of n needs to be not just asymptotically non-negative, but asymptotically positive. Question? The screen isn't on. Oh, for crying out loud. Why isn't it on? I know why it's not on. So you're all just kind of secretly laughing at me as I'm pointing to things. And it's not plugged in. You know why it's not plugged in? Because there's 50 million people up here earlier, and I couldn't plug it in. It's your fault. Sorry. Well, it's there it is. Okay, there's the mass. There's this. I'm just reviewing what I said before, and I'm just looking at the notes that were posted last time. Okay. A subproblems, each of size 1/b the original. F of n is the cost of dividing and recombining. F of n here needs to be asymptotically positive. Okay, so let me state the master theorem. Let A greater than or equal to 1, B greater than 1, F of n asymptotically positive. That means that for a sufficiently large n, f of n is a positive number. There's a last time that it even touches the n-axis, the horizontal axis. Let T of n be defined by T of n equals A T of n over B plus f of n. Now, let's not worry about the fact that that doesn't actually define a function, because I haven't specified what constant it bottoms out, or constants it bottoms out to, and what the crossover point is from the recurrence to the constant. And for that matter, whether this is supposed to be floor or ceiling, it's part of the content of the theorem that those things don't matter to the conclusion. Right? Those things, and we've already seen that explicitly in an example. You can change those things, change floor to ceiling, you don't get a different asymptotic solution. So, given that, we have three cases. One, now look, these three cases are going to look a little bit complicated, but once you start to digest them and start to sort of absorb their meaning and use them in a few examples, it becomes very easy to see what's happening, what they're about. We'll do that slowly. If f of n is in the class big O n to the power log base b of a minus epsilon for some positive number epsilon, then T of n is in the class theta n to the power log base b of a. That's case one. Two. Case 2, if f of n is in the class theta of n to the power log base b of a, then t of n is theta n to the log base b of a times log n, or what's the same thing, f of n times log n. Right, the reason they're the same is because f of n and these two functions, that factor and that factor, are asymptotically equivalent, right? Each is a tight asymptotic bound on the other, so you can put either one you want. And then case 3, this is the most complicated. If f of n is in the class big omega, n to the power log base b of a plus epsilon for some positive number epsilon, and if a little bit more, a f of n over b is less than or equal to c f of n for some c in the range 0 to 1, strictly within that interval, and all sufficiently large n, so for large enough n, then t of n is in the class theta f of n. Okay. Well, it seems like a lot there. It's not hopeless. First of all, let's just look at the whole thing. Can it all be seen? Just about. Almost all. No, it doesn't quite fit, does it? Well, let's just put it like that. The first thing I want to point out is that the conclusion in each of these three cases, the thing after the then, is a tight asymptotic bound on t of n. T of n is theta of something. T of n is theta of something. T of n is theta of something. So the master theorem gives you asymptotic solutions only. Doesn't give you exact solutions to recurrences. And I talked last time about the distinction between those two things. Doesn't give you the actual function that satisfies the recurrence. Gives you its asymptotic growth rate, which is good enough for in-algorithm analysis. Okay, and in each of these three cases, cases is an if-then statement. The thing after the if is a question about the asymptotic growth rate of f of n. If f of n grows this fast, if f of n grows this fast, if f of n grows this fast. So in all cases, we're comparing f of n to a certain function. The function is n to the log base b of a. So let me remark on that. We compare f of n to n to the power log base b of a. Now, a and b are fixed constants. So log base b of a is just a number. So that function is just a polynomial. right? It's just that its degree is written in a weird way. So don't get freaked out by the fact that you have n to the power log blah, blah, blah. You're going to lose it or something, right? We're always comparing f of n to a polynomial. When f of n is itself a polynomial, doing this comparison is trivial. It's really easy to see. Furthermore, what we're asking is, who is the winner in this comparison? There's like a race between these two functions, and the question is, which one wins? Which one is the faster growing, or the worse, in algorithmic terms, which is the worst function? The faster growing function is the one that's going to dominate the recurrence and is going to give you the answer. For instance, in this case, f of n is bounded above by something a little bit weaker than n log base b of a. So think of epsilon as a small number, right? Epsilon is thought to be a small number near 0. So this is a polynomial whose degree is a little bit less than log base b of a. Since f of n is no faster growing than a polynomial that's a little less fast, then we can say that n log base b of a is the winner. And furthermore, it wins by a polynomial factor. The polynomial factor is n to the epsilon, right? Because it loses to something that is polynomially slower than n to the log base b of a. So, in each case, the winner meaning the faster function or the faster growing function determines T of n, or the asymptotic solution. And the winner must win by a polynomial factor. The factor being n to the power epsilon. So in other words, in case 1, if I take n log base b of a, n to the power log base b of a, and I divide it by n to the epsilon, it gets weaker. And f of n can't get past that slightly weaker function that's polynomially slower than n to the log base b of a. So n to the log base b of a won, and it won by a polynomial factor. Therefore, T of n is theta of the winner. That's what case 1 says. This only needs to be true for one epsilon. But of course, if it's true for one positive epsilon, it's true for any smaller epsilon, because those are smaller polynomial factors. If you win by 10 yards, you're running a race, and some guy wins by 10 yards. Well, then you also won by 5 yards, right? You're also at least 5 yards away from winning. You see what I'm saying? A smaller epsilon also works. Okay, let's look at case 2. Case 2 is a tie. F of n and n to the log base b of a are the same growth rate. So those two functions are tied, and in that case, the winner, and there's no winner, does determine the outcome, except in case 2, there is this unexplained log factor, and I can't explain that log factor without showing you the proof of case 2. Now, maybe you'll be relieved when you hear that I'm not going to go over the proof of this. I have a sketch of the proof of case 1 in the handout, which I will not cover in class in the interest of time. The book has what I would call a sketch They call it a proof. I would call it a sketch of a proof of the whole thing, which you can read. If you want to see that covered in class, take either 102 or the graduate version 201. 102 is algorithm analysis, and 201 is graduate algorithm analysis. I usually try to provide some level of proof in those two courses. I'm really interested in this course in you being able to use this theorem, not prove it. So we're not even going to cover the proof in class. Except I'll tell you what the proof is. The proof is the iteration method on steroids. We do the iteration method, but everything in it is general, right? I don't have a specific function f. Just have the letter f of n. I don't have a specific number a or a specific number b. So we try to do the iteration method in full generality, and that's what produces these three cases. Okay, and that's the way you should approach it if you try to read the proof in the book. All right, so f of n is, or rather, case 2 is when f of n and f of n and n log base b of a, those two functions tie in their growth rate. So it's that common function times log n. The log n really comes from the proof. That's the asymptotic growth rate of t of n. 3 is more complicated because in this case, f of n is bounded below by something that is n to the epsilon stronger than n to the log base b of a. So this is n to the log base b of a times n to the epsilon. So in this case, f of n is the winner, and it's winning by the polynomial factor n to the epsilon. Okay? Again, any smaller epsilon will do, but all that's necessary is to verify that it works for some positive epsilon. But in addition to checking that hypothesis, we have this added condition. Let me put it in a box. I refer to this, and the book refers to it as the regularity condition. It looks kind of complicated, but it says there has to exist a positive c in this range and sufficiently large n for which this inequality holds. And it's in principle, in practice, this is usually a trivial thing to check, but you do have to come up with a particular c to check it. All right, so how do you use, and by the way, again, the winner, who won by a polynomial factor, dominates the recurrence, and t of n is theta f of n in this case. F of n wins. So, case 1, n to the log base b of a wins. Case 2, it's a tie. Case 3, f of n wins the contest. Now that you know that, you could almost just stare at the recurrence. I mean, those three pieces of information, a, b, and f of n, are all that you get. And that's all you need in order to determine an asymptotic solution. So you'll get pretty good at just looking at such problems and immediately seeing who the winner is and just write down the asymptotic solution. However, when you do these problems on an exam, like midterm 2, I insist that you tell me which case you're in, and in case 1 and 3, you tell me a particular epsilon that makes this statement true, and then you're at liberty to write down the answer. That's case 1 and 3. In case 2, you just verify that this is a true statement. You have to say why, maybe by taking a limit or something. And then you get to write down the answer. In case 3, you not only have to give me the epsilon, but you have to verify the regularity condition. So give me a c, or give me a range of values of c that will work. Okay. One more thing I'd like to say before we look at examples, and that is that notice all of these hypotheses pertain to the asymptotic growth rate of f of n, not the function f of n itself. So you can always simplify your recurrence. Here's the original recurrence. So if that's some kind of ugly, complicated function, and you can simplify it to a single term, like n to the 3/2 or something like that, do so. Because the hypotheses that you're checking only care about its asymptotic growth rate. So any function that's asymptotically equivalent to f of n would necessarily satisfy the same conditions. All right. So let's look at examples. Yes. What did I forget now? Okay, I just think what everything's off. I don't know. Go ahead. Why does case 3 need the regularity condition? All I can say to that is you have to look at the proof. Right? I mean, yeah, it's like, why is that log? So, oh, by the way, yeah, what's this log doing there? You might as well ask that. I can't answer it without trying to launch into the proof. Notice that I don't specify the base of that log. Of course, right? Because base of a log doesn't matter when you're talking about asymptotic growth rates. This base you must satisfy because that base determines a specific number, and that's the degree of n, the degree on n, the power on n, if you will. And that degree, is critical in determining how fast n to the log base b of a is. All right. So, first example. Yeah. Okay, here we go. T of n equals 8 t of n over 2 plus n cubed. Okay. So what are we supposed to do? Compare n cubed, that's f of n, to n to the log base something of something. Log base b of a, log base 2 of 8. What's log base 2 of 8? 3, because 2 to the 3 is 8. So this is n to the 3. Not only is it a tie, but they're the very same function. They're not just asymptotically equivalent, they are one and the same function. So what case are we in? By case 2, t of n is theta. This function, or this function, doesn't matter which because they're the same, n cubed log n. Voila, that's it. You just write down the answer. Well, case 2 is the nicest case because there's very little work to do. Once you see that it's a tie, once you can, and I guess I didn't prove that it was a tie, but I think it's pretty obvious that it's a tie. Once you see that it's a tie, you can just write down the answer. The other two cases, you have to dream up this epsilon. So let's look at t of n is 5 t of n over 4 plus n. So what are we supposed to do? Compare let me put a box around the answer. This is nice. We get answers. We're computing answers, so let's put boxes around them. Okay. So compare f of n, that's n, to n to the power log base 4 of 5. Now, I'm comparing a polynomial, n to the 1, to another polynomial, n to the power log base 4 of 5. What's bigger, 1 or log base 4 of 5? What's bigger, 4 or 5? 5. So what do I have to raise? When I raise 4 to something and get 5, the something I'm going to raise is bigger than 1, right? The power on 4 that gives you 5 is bigger than 1, because 4 to the 1 gives you 4. 4 to something bigger than 1 gives you 5. So this number is bigger than 1, so this is the winner. So note, 4 less than 5 implies 1 is less than log 4 of 5. I don't need a calculator, by the way, to figure that out, but this is the kind of thing that people like to have calculators for. But it's not always necessary. Okay, so what case, if I'm in any case at all, what case must I be in? The winner here is n log base b of a. Which case had that as the winner? Case 1. That was case 1. Okay, so we're in case 1. So in case 1, I've got to find an epsilon for which n is big O n to the log base 4 of 5 minus epsilon. The nice thing about comparing a polynomial to a polynomial is there's a ready choice, always a ready choice for epsilon. Let epsilon equal the difference between these two degrees, the larger minus the smaller. Log 4 of 5 minus 1. So, because of this inequality, epsilon is greater than 0. Then epsilon is greater than 0, and what? Well, let's rearrange that. Pull the 1 over to the left and the epsilon over to the right. So if I do that, I get 1 equals log 4 of 5 minus epsilon. Therefore, n is equal to big O of n, right, n to the 1. Every function is big O of itself. Never forget that. But 1 is this number. So this is big O n to the power log 4 of 5 minus epsilon. Exactly the expression I wanted. F of n is big O n to the log base b of a minus the epsilon that I picked. The epsilon that I picked better be positive too. Okay. By case 1, we get T of n is theta of the winner, n to the log base 4 of 5. Put a box around the answer. Okay? This can be very easy and can go very fast, especially on an exam, once you get the hang of it. So don't be intimidated by the seeming complexity of a theorem like this. There are a few things, it's just telling you exactly what you need to check, and then exactly what answer you get. It's literally a cookbook method. You push a few buttons, you get an answer, you write it down. Okay, example. Well, I've done a case 2, the easiest case. A case 1, the next complicated case. The most complicated case is case 3. So this is T of n equals 5 T of n over 4, just like before, plus n squared. So the difference between these two examples is here I had n to the power 1, now I have n to the power 2. Okay? So we're supposed to compare n squared to n to the log base 4 of 5. Since I'm comparing these polynomials, comparing the functions amounts to just comparing two numbers. The number 2 and the number log base 4 of 5. Now, let's see, which is bigger? I already know that log base 4 of 5 is bigger than 1, but is it bigger or less than 2? It's less than 2. Why? Huh? Can somebody give me a reason other than turning on your calculator and checking why log base 4 of 5 is bigger than 2? Yes? I'm sorry, is less than 2. Yeah? Because 5 is less than 16. That's why. So note, 5 less than 16 implies, just take log base 4 of both sides. Log base 4 of 5 is less than log base 4 of 16, which is 2. All right, so that tells me that this guy is the winner, so I must be in case 3, if I'm in any case at all. So, again, anytime you're comparing polynomials and you need to figure out what the epsilon is, always have it be the difference of the 2 degrees. That's actually the largest epsilon that'll work. Anything smaller than that epsilon will also work, but nothing larger than it will work. You can verify those facts. So let epsilon equal larger minus smaller. Then epsilon is greater than 0 because of this inequality. And let's rearrange the inequality. 2 equals log 4 of 5, or rather, rearrange that equation, plus epsilon. So, n squared is omega n squared, right? Every function is omega of itself. But 2 is equal to this thing, omega n to the log 4 of 5 plus epsilon. Okay, so I've checked the first hypothesis in case 3. F of n, right here. F of n needs to be omega n to log base b of a for some particular positive epsilon. We've named the epsilon, and we showed that this is true. And it's triviality to show it, especially when f of n is itself a polynomial. When f of n is not a polynomial, it's a little bit more, it takes a little bit more thought. But let me just put it this way. When it is a polynomial, don't fail to notice that you have an easy problem before you. Okay, but there's more in case 3, and that's the regularity condition. Must also show so we have to check the regularity condition holds. A f of n over b is less than or equal to c f of n for a c in the range 0 to 1. So let's just write down that inequality. F of n, the f is the square function. A is 5, b is 4. So I need to show that 5f of, 5n over 4, the quantity squared, is less than or equal to cn squared for some c in the range 0 to 1. Okay. Well, let's play around with that inequality. This would say 5 over 16 n squared is less than or equal to cn squared. Wouldn't it? That's true for not just for all positive c, not just for all sufficiently large n, but for all n, all positive n at all, right? N just needs to be bigger than 1, and this is true. So in fact, we can cancel n squared from both sides of this inequality. So this is the same as 5/16 less than or equal to c. Well, this gives me a range of values of c that will work. So, therefore, pick any c in the range 5/16 less than or equal to c, but strictly less than 1. Now, is it possible to find such a c? Well, that all depends on the fact that this fraction 5/16 is itself less than 1. If it weren't less than 1, then there would be no space in between these two. The 5/16 would, if it were somehow bigger than 1, there'd be no c to pick, and the regularity condition wouldn't work. So, this is possible since 5/16 is itself less than 1. But that follows from the original inequality. So the same inequality that put us in case 3 is the one that makes the the regularity condition work. That's not an accident. Does that mean the regularity condition will always be satisfied? Can we just forget about it now? The problem is, I can only say that it'll always be satisfied if f of n is a polynomial. If f of n is not a polynomial, it's a trickier matter, and it need not be satisfied. So let's just say at this point the regularity condition is satisfied, because such a c exists. By case 3, t of n is theta of the winner. The winner is f of n in case 3, and that's n squared. Okay, so we've done exactly one example from each case. All right, so let me say it again. The conclusion of the master theorem does not change if we replace f of n by an asymptotically equivalent function. And the only thing we'd want to replace it by is something simpler looking. So, for instance, if I took t of n equals 8 t of n over 2 plus 10n cubed plus 15n squared minus n square root n plus n log n minus 1. So if I were to have something ugly like that, I notice that f of n, this big ugly function, is in the class theta n cubed. So this is the same thing as t of n equals 8 t of n over 2 plus n cubed. So the first step should be simplify this function as far as you possibly can. And we already did this. This was our first example. By case 2 was t of n is theta n cubed log n, I believe. Because you can see it now. 2 to the 3 is 8. So log base 2 of 8 is 3. So it's a tie. So we're in case 2. The common function times the extra log n factor. Okay, so that's one thing I wanted to say. Often, when you, because of this, since it really only, it doesn't matter what f of n is, it matters what theta f of n is. Often we write the recurrence as this: t of n equals a t of n over b plus theta f of n. Often, you just put that symbol in the recurrence itself, emphasizing the fact that it doesn't matter. There's a whole class of functions here that you could put here, and you get the same answer, the same asymptotic solution. I don't know if our book does it, maybe in a few exercises, but every once in a while you'll see a recurrence written this way. It's a tip-off, since we're not specifying the function, that we're only looking for an asymptotic solution, and we're going to use the master theorem. Okay. So here is an exercise, and it is essentially what I just told you a minute ago about case 3 and the regularity condition. Prove that if f of n is a polynomial or polynomial growth rate, I guess I should say, and if degree of f is greater than log base b of a, so f of n is the winner. And since they're both polynomials, it wins by a polynomial factor. Then case 3 holds, and the regularity condition necessarily is satisfied. This is going to be probably a homework problem. If not the next homework, probably the one after that. And I have put this on midterms and final exams in the past, so it's an exercise well worth doing. It's just a generalization of the last example where I did case 3. The same inequality that put us in case 3, in that case, here it is in general terms. That's the inequality that puts us in case 3. That same inequality forces the regularity condition to be satisfied. So in our case, it made this fraction strictly less than 1 so we can fit a c in there. That's what always is going to happen. What I'm asking you to do is prove that. Okay, what else? All right, so let's look at more complicated examples. First, t of n equals t of floor n over 2 plus 2 t of ceiling n over 2 plus log n factorial. Okay. The first thing we should always do with a recurrence is simplify it. Simplify it for use with if all we're looking for is an asymptotic solution, we should simplify it with the goal in mind of using the master theorem. First thing I have to do is remember that floors and ceilings don't matter. If I erase the floors and the ceilings, these two terms can be combined. We can simplify this to t of n equals 3t of n over 2 plus, we can replace that thing by something that's asymptotically equivalent to it. Log n factorial is a little complicated. Do you know of something simpler than that? That's theta of log n factorial? N log n. And by whose formula? by Stirling's formula. So we learned that, right? And did I put that on the exam? No, I put the other one on the exam. We'll probably put the log n factorial, that's going to be fair game for the final now. Okay, so this can be replaced by n log n. Okay, so we first simplify it. Now what? Now f of n is not a polynomial. I haven't looked at one like this before. Compare n log n to n to the power log 2 of 3. Okay, so I'm comparing something that's not a polynomial to something that is a polynomial. Except the log factor, remember I told you this, because of L'Hopital's rule, log factors are kind of like infinitesimals. So multiplying n to the power 1 by log n is making it infinitesimally stronger, just a tiny bit stronger than n. I mean, it goes to, this function is little omega of n, right? N is strictly weaker than this, but the distance between the two is infinitesimal. So that means as far as finding the epsilon goes, I ought to just pretend like that log factor isn't there. If the log factor wasn't there, I would compare the 1 to the log 2 of 3. So if I compared the 1 to log 2 of 3, who would win? Log 2 of 3 is bigger. Okay. And without that log factor, I would say then that I'm in case 1, because n to the log base 2 of 3 is winning. It's still winning because this log factor only makes that infinitesimally stronger, not polynomially stronger, like this is. Okay. So what would I choose the epsilon to be if that log factor wasn't there? I would choose it to be log 2 of 3 minus 1. All right, turns out that that won't work, right? Choosing epsilon to be log base 2 of 3 minus 1 won't work. Anything smaller than it, though, will work. So let epsilon equal log 2 of 3 minus 1. I need anything smaller than that. The simplest number I can think of that's smaller than that is half of that. 1/2 log 2 of 3 minus 1. Since log 2 of 3 is bigger than 1, epsilon is a positive number. Since 2 less than 3 implies 1 is less than log base 2 of 3, we have epsilon positive, right? Because the thing in parentheses is positive. 1/2 a positive number is a positive number. Yes?
How do we know that log base 2 of 3 minus 1 doesn't work?
I'll show you that it doesn't work when we finish, because I want to first give you the one that does work. And then I'll show you that without the 1/2 it wouldn't work. I mean, you're just basically taking my word for it at this moment. But I will get to that. Okay, so let's rearrange this equation. I have 2 epsilon equals log base 2 of 3 minus 1. Let's take the 1, let's see, pull it over to the left, and one of the 2 epsilons, pull it over to the right. So I get 1 plus epsilon equals log 2 of 3 minus epsilon. Does everybody see that? I took one of these two epsilons, pulled it over to the right, leaving one on the left, a negative one on the right, and I pulled the negative one over to the left. It became positive 1. I know I need this expression because that's what's in the exponent in case 1. How am I going to verify that big O holds in that case? Well, first of all, observe that f of n, that's n log n, over n to the power 1 plus epsilon is equal to n log n over n times n to the epsilon. The n's cancel. And if I take the limit of this as n goes to infinity, what do I get by L'Hopital's rule? Forget L'Hopital's rule. I've got a log against a polynomial. Who wins? Polynomials always win, and it doesn't matter how small the degree is. The degree can be as small as a positive number you like. Another way to look at that is, this is what I mean when I say log n is infinitesimal, right? It's like a number. It's like a polynomial whose degree is not 0, but smaller than any positive real number. That's what's meant by the word infinitesimal. By the way, that's kind of the conundrum that drove people crazy around the middle 1700s about the foundation of calculus, right? Limits, and so it's only about 100 years after that they even defined the notion of a limit. Right? People were doing calculus before they ever did limits. Isaac Newton and Leibniz. Right? They're basically in their heads they're taking limits, but they never explained to anybody what a limit was. So there was a lot of controversy. Then instead they rattled on about infinitesimals. It's a useful concept, right? A number, so this is like n to an infinitesimal power. Right? And that's what L'Hopital's rule tells us. This goes to 0 as n goes to infinity. Okay? Well, that means the top is little o of the bottom. N log n is little o of n to the 1 plus epsilon. But any function in little o is also in big O. Little o is a subset of big O, n to the 1 plus epsilon. But 1 plus epsilon is exactly that expression. So this is big O of n to the log 2 of 3 minus epsilon. And that's exactly the comparison that I have to do in case 1. See how that fit together nicely? Therefore, by case 1, T of n is theta of the winner that won by a polynomial factor. That's n to the power log 2 of 3. Okay. Now, I invite you to check that any other number, positive number less than this, would also have worked. For instance, try 1/3 log 2 of 3 minus 1. That would also work. Okay, but somebody asked me to show that epsilon equals n to the log 2 of 3. I'm sorry. Epsilon equals log 2 of 3 minus 1 does not work. We're doing on time. We've got 2 minutes. Just enough. Yes, go ahead. Real quick. Yeah?
Subset of big O and
Little o is a subset.
yeah, one more to the right is
Epsilon. Yeah. Right, that is just this equation right here. Sure. Okay, so let's check that this does not work. Suppose I picked that as epsilon. Then I would have, certainly epsilon is greater than 0. And I would have 1 equals log 2 of 3 minus epsilon. But what would happen if I now take n log n over n to the power log 2 of 3 minus epsilon? That would be the same as n log n over n to the power 1 because of this equation, right? That exponent is the same as the 1. But then the n's would cancel, and this would go to what? Infinity. And this would give us, therefore, that n log n, when you get infinity, that says that the top is little omega of the bottom. N to the log 2 of 3 minus epsilon. But that's exactly the opposite of what we want. If I got a function in little omega, it is not in big O. So therefore, n log n is not in big O, n to the log 2 of 3 minus epsilon. So this shows that that particular choice of epsilon would not work, and nothing bigger than it would work. Okay, well, I want to point out before you go, let's see, there is a new handout. And it gives nothing but, if you look in handouts, it is master theorem problems. So a bunch of problems. That handout wasn't written by me, by the way. Bunch of exercises involving the master theorem. You can start in on that if you like. Please spend 5, 7, 8 minutes, no longer, rifling through these papers and trying to get your midterm off my hands, because I don't want to carry them back.